All right, today we're going to finish up talking about rates of change, and the concept that we have been leading up to has a special name and a very special place in calculus. The name of this concept that we have been leading up to is called the derivative. Okay? Because there are many real-world situations where, we look at how things change as we look at the x-coordinates and the original y-coordinates. I mean, that's very common. We can look, there's all kinds of word problems that deal with that. However, there's a whole nother branch of problems where we don't want to necessarily consider the x and the y-coordinates, but we want to consider the x-coordinates compared to how they are, the rates of change. How are the y-coordinates changing? Okay? Or in other words, what we've been discussing, how is the slope of a function changing as time goes by? And so this whole nother branch of problems, that's what we'll be looking at here in the calculus part of the course, which is dealing with the derivative concept. Okay? The easiest thing that I can tell you in terms of a derivative, there's lots of other words that basically mean the same thing. Okay? What we studied last time called instantaneous rate of change is basically the same thing as a derivative. So we will be doing very similar calculations. Okay? Another really easy word that we could substitute in here for a derivative is slope. If you can just think about the derivative as the slope, that's another good way to remember what a derivative is. Okay? Now, calculus, yes, we have a formal definition and a new symbol, so I want to put this up here as well. Okay? Whenever you see in your textbook or in any workings of calculus, you ever see this f prime of x. This looks like an apostrophe, but it's f prime of x is how we read it. This is saying, I don't really care about the original function f of x, I am caring about its derivative. Okay? So this is the derivative function, f prime of x. Okay? The definition for this is the same definition we had the other day dealing with instantaneous rate of change. And what it says is that we want to take the limit as h gets really small of this difference quotient here. Okay? And let me just review real quick what this definition is really telling us. First of all, the calculation for this, we decided the other day, was really close to a calculation for slope. In fact, that's what it is. It's a slope calculation. Okay? This is the second y-coordinate minus the first y-coordinate. And in the denominator, we have the second x-coordinate minus the first x-coordinate, but it just simplified a little bit. And the difference between the x-coordinates was just what we called h. And our goal in this calculation of limit, we want that difference in x-coordinates to get really, really close to 0. We want to try to make that difference as small as possible because that's how we get a good idea of what the slope is at that function, or at that point on the function. Right? So this is our definition that we will be using here today. Now, let's go ahead and pick an example and work through this calculation. An example a little different than the ones that we had the other day here. What if we work through this example? What if I've got this function f of x defined as 2 divided by x? And I want to calculate the derivative of this function. Or in other words, I want to calculate what's the slope equation of this particular function. Okay? So that I can predict slopes. You know, what if I want to know what's the slope of this graph at 3? Or what's the slope at 5? Or any other value? Then I will have a slope equation that I can plug that particular coordinate into. Okay, well, here's how we work. F prime of x, we're going to calculate this difference quotient limit. Okay, limit as h goes to 0. What is the function evaluated at x plus h? This is the function evaluated at x. I'm just going to take 2 divided by whatever my number is. So what's the number? Yeah, what's the function at x plus h? 2 divided by x plus h. Okay. Instead of evaluating the function at x, I'm now evaluating it at a number just a little bit to the right of x plus h. Okay. Second part of my definition says to subtract the original function f of x. So I just take minus 2 over x, and then the denominator is just an h. Okay. Now my goal becomes, it just turns into a big algebra problem. We need to simplify this particular problem, and our goal in the simplification is to eventually get some h's to cancel off so that we don't get 0 divided by 0 anymore. Right? All right. Up in the numerator, what do I need to come up with in order to be able to simplify this? Common denominator, exactly. Okay. What we talked about, I think, the very first day of the course, just a little bit of algebra review. Okay. What component is missing from this denominator? I'm going to wait on that one for just a second. What about just up here in the numerator? What's missing from my common denominator? I'm missing the x term, right? Okay. So I'm missing an x term, so I'm going to multiply the top and the bottom by x. What am I missing from this one over here? X plus h. So I'm going to multiply both numerator and denominator by x plus h. Now as I look at my equation, I see that I have the same denominator in both locations. I can join this together as one single fraction. And here's what it will look like. The denominator of that fraction will be x times x plus h. Okay? And up in the numerator, well, let's just kind of look at it here. We can simplify it as we go. If I just look at the numerator, notice the negative sign goes through to the second piece. What cancels off here? The 2x's, right. I have a positive 2x, and here I have a negative 2x. So those pieces will go away. What's the only thing that will be left up in the numerator then? A negative 2h. Now be careful, I'm skipping a little bit of the work here, but the 2 still distributes through to the h, and the negative still distributes through. So I still have a negative 2h left over in the numerator. Okay? All right, now the last thing to worry about, what do we do with this h on the bottom? What if we try to just make this one fraction without, 2 divisions in it? What if we just try to simplify it a little bit? Okay? Yeah, what we're going to do is in the denominator, again, this was a big division sign here a little while ago. If I want to get rid of this h in the denominator, what I can do is I can multiply both the numerator and the denominator by 1 over h. And my purpose in doing that is because now the h's will cancel in the denominator, and so I have eliminated this whole piece below the big division sign. Okay? It's now all just divided by 1, and we don't have to write division by 1. Where does that put the h then? Does it put it up in the numerator or in the denominator? Well, it puts it in the denominator, doesn't it? Okay? Now, so the h really goes here. You won't have to do this multiplying by 1 over h every time. After you do a couple of these, you're just going to recognize that this h always ends up in the denominator when we clean it up. Okay? But just this first time, I wanted to show you what's really going on. Okay, this is good because now what actually cancels off? I now get the h here to cancel with this h, and what I have left is negative 2 over x times x plus h. Okay? This limit actually goes through the whole problem, but I usually just don't rewrite it until I get to the very end. Okay? Now I want to take the limit as h goes to 0. In other words, I'm going to substitute in 0 for the h's that are still in the problem, and what will I get when I simplify that? Negative 2 over what? X squared, right, because this will just be an x inside of here. X times x is x squared. This is what we call, whoops, let me put the notation here. This is what we call f prime of x. This is the derivative function for 2 divided by x. Okay? Now, the follow-up questions that we can answer, now they say, the next question might be, what was the slope at x equals 3? And in this case, what would the answer be equal to? Negative 2 over 9, because all I do is substitute in 3 into this function, and I end up with negative 2 divided by 9. So I know that the graph must be doing what at x equals 3? If I have a negative slope, what does that mean is happening on the graph? If you have a negative slope, what has to be happening to the y values? Don't they have to be decreasing if you have a negative slope? Okay? So I know for sure on this graph that it is decreasing when I'm at x equals 3. Okay? If you want to pick a different example, well, in fact, let's talk about this real quick. What will be happening on this entire graph? if we look at this a little bit closer here, okay, what type of numbers do we get when we square? Okay, these will get bigger and bigger, but for sure they will always be positive numbers, won't they? Okay, this is always a negative number. So what happens when you divide a negative number by a positive number? It's always negative. So therefore, no matter what number I choose to sub in here, I will always get a negative answer. So that tells me my graph is decreasing for the entire graph. Okay? And so that's the type of analysis that we'll be doing, mostly as we get into the next chapter, but I just saw a good example here. I could kind of interject that little comment there. Okay? So this is one example of finding a derivative or finding a slope function. Okay? All right. Another similar question. Let's try another one here. All right, what if our original function is f of x equals 3 times the square root of x? The question says, write the equation of the tangent line at x equals, let's just pick 1. Okay. In other words, just off to the side here, if I was to draw a rough sketch of 3 times the square root of x, if you plot that on your calculator, it'll look something like this. Okay, square root functions all kind of look the same. What we are after is, if we get over here to x equals 1, and we draw what's called the tangent line, in other words, the line that only hits it in one point, what's the equation of this line? Okay? Because again, when we get into the applications of calculus, this equation, we will need to know what it is. Okay? All right, now, in order for me to write the equation of a line, I have to know 2 things. One of them is the slope. And how do I find the slope when I'm given an equation? Well, we find its derivative. Okay, so that's how this all ties together. We still need to calculate this difference quotient because we need to know the slope. Okay? All right, so again, we will set this up. F of x plus h minus f of x all divided by h. And again, this will be something that as you're working on your homework, you probably won't have to rewrite this every time, but just so I can refer to things on the board, it makes it a little easier for me. Okay? All right. In our particular equation, 3 square root of x, what is the function evaluated at x plus h? 3 square root of x plus h, exactly. Instead of evaluating it at x, I'm now evaluating it at a point just a little bit to the right of x. Okay? Minus the function at x, which is just 3 square root of x, all divided by h. And again, my goal is this becomes an algebra problem. How do I simplify this difference quotient? Okay? What's been our technique we've used for square roots? Times the conjugate, exactly. All right, so over here on the side, let's go ahead and write the conjugate. What is the conjugate of the numerator? 3 square root of x plus h plus 3 square root of x, sure. And I'll have to multiply by the same thing on the denominator just to keep my expression balanced. Okay, I'll go ahead and put some parentheses around here. Even you can kind of imagine them there even if you don't. We need to FOIL out the numerator to see what this equals. All right, when I take the first term times the first term, okay, first of all, what number do I get? 9. And when you multiply the square root of x plus h times itself, what do you get? X plus h. Okay, we've seen examples similar to this earlier on in the semester. Okay, what's the other advantage of multiplying by the conjugate? What happens to the outside and the inside? They cancel. Okay, so I'm not even going to write anything down because hopefully we know that by now, that outside and inside cancel. That's the whole reason we changed the sign here, so that happens. Okay? And then we've now multiplied last times last. And what is it? Minus 9x, sure. Okay? The denominator, I probably don't want to simplify it too much. I'm just going to rewrite it as h times that conjugate piece. We only want to simplify in the numerator. I mean, that's the reason we multiply by the conjugate. up in the numerator because that's the part we needed to simplify. It was the more complicated piece. Okay. All right, I'll move over here to the left so I can keep this down here and I won't be walking across the board. The numerator actually simplifies a little bit to what? Yeah, the 9x here will cancel with the negative 9x, so those are gone. The only thing left is a 9h, isn't it? Okay. And then, yeah, I mean, we can save a couple of steps here. We have a 9h left over in the numerator. The h from there will cancel with the h from here. And so now let's go ahead and write what would be left then. I would have just a 9 up in the numerator, and in the denominator I have this conjugate piece. So 3 square root of x plus h plus 3 square root of x. Okay? All right, and now we are ready. Now since we've had the h's cancel in the numerator and denominator, now we are ready to take this limit as h goes to 0. We can actually sub in 0 and get a decent answer. Okay? And when we do that, we get 9 divided by 3 square root of x plus another 3 square root of x because the plus 0 goes away. If this is an odd-numbered question in your book, they will probably simplify it one more step. This is what down here? 6 square roots of x. I got 3 of them here, and I got another 3 of them. That would be 6 of them. So they would probably simplify it this way. And then, in fact, since 9 and 6 have a common factor, they'd probably go one more step. If I cancel off a 3 from each component, they would probably write it this way. 3 over 2 square root of x. Just doing all the simplification that's possible. And again, this is what we call the derivative function. Okay? Takes a lot of work to get to it. Okay? But now that we are here, we should be able to answer our initial question very easily. Okay? We want to find the slope at x equals 1. So if I substitute in 1, what is my slope? 3 over 2. All right, so one of the components that I need to be able to write this equation is the slope, and the slope is 3 divided by 2. What's the other component that I need to be able to write an equation? Well, I need some ordered pair, whether it's the y-intercept or some other number. Okay? Well, I don't necessarily know the y-intercept on this graph. Okay? So I'm just going to go for some other point on this graph. Okay? I'm going to go ahead and choose x equals 1 because that's the point that I'm concerned with here. If I substitute 1 into the original function, what do I get for a y value? 3. So in other words, this point that we are concerned with has the ordered pair 1, 3. Okay? Now, if we remember back, how do we write the equation of a line when we know the slope and we know some other point? Yeah, we got y minus y sub 1, in other words, y minus this y coordinate, equals the slope times x minus the x coordinate. Okay? And so this is the equation of our line that we have for the tangent line. Again, the book may want to go through and simplify this. They may want it to look like mx plus b. So what could be done to simplify this is you can actually distribute on the right side here. So I would have 3 halves times x. I would have negative 3 halves when I multiply this through. And then if I add that 3 over to the right side, okay, I'll just do the math in my head here. I believe it should be 3 halves. Okay, because I got a positive 3 and I'm subtracting 1.5. That leaves me with another 1.5. So this is one way the answer may be written. This is also okay. When you get to your exam and you're writing the equation of a tangent line for me, you can leave it in this form if you want. You don't necessarily have to simplify it to mx plus b. Okay? All right. So there's the example of a couple of examples of derivative. Okay? And like I said, this is not the easiest thing we do. We will learn some better shortcuts for certain types of equations later, but the thing is, if we don't have a shortcut for a certain type of equation, this is what we have to fall back on. Okay? And so not the nicest thing to work with, but it is an avenue we can use. The next thing I want to point out is that there are certain times when the derivative does not exist. And I want to just kind of make a listing of where the derivative of a function would not work or would not exist. I'm going to put a diagram up on the overhead here as well. And I can point to some examples. Switch to the correct mode. Okay. Here's a possible example of a graph, okay, a really weird looking graph, okay, but it's a good example of where a derivative would not exist. Now again, remember, a derivative is just a slope. So where along this graph would a slope not exist? Okay? Well, if I start down here on the left side, I have slope values. You know, I could find a value for the slope all along here, but what happens up at this point here where I have a really sharp turn? Okay? Well, let's look at this a little closer here. Okay? If I have a really sharp turn, that means my slope is positive on one side, and then what happens as soon as I jump across the sharp turn? Now my slope's negative. Okay? And so this is one place where we do not have a derivative, is if we ever run into a sharp turn on a graph. Okay? Then we will not have a slope, because one side will have a positive value, and then all of a sudden on the other side it jumps over to negative. You know, the limits won't match up, okay, in terms of those slopes. Okay? Now, what do I mean by a sharp turn? Now, how sharp is a sharp turn? Okay? This is considered a sharp turn right here, whereas notice this piece right here in the second part, it has negative slopes, but then it smoothly changes over to positive slopes. So like x squared or parabolas, those would be considered smooth curves, and those actually do have slopes everywhere. Okay? So that's what I mean by a really sharp turn. A good example of a sharp turn would be the absolute value function. Y equals absolute value of x is just that V shape. That's too sharp of a turn. Okay? All right. Second place where we can end up with a derivative not existing. Any places where the function is discontinuous. Okay? And what I mean by any places where the function is discontinuous, any jumps in the graph, like we have right here, we will not have a slope, because up here we have a certain slope, down here we have a different slope, and then they may not agree with each other. Okay? Any places where the graph has a vertical asymptote, we will not have a slope, because over here I have a really high slope, and over here I have a really negative slope. So again, the values just do not agree. Okay? And this darn thing came up here again, but down here there's an open circle or just a hole in the graph. That again, if the function's not defined there, if it's discontinuous, we can't have a slope. Okay? The last place is what we call a vertical tangent. Okay. All right, and the example that I will give, I mean, over here on the graph we can see what a vertical tangent looks like. It's where the graph is really, really steep. Okay? But the reasoning or the rationale behind that is this. Okay? In algebra, when you were told to look at the slopes of certain graphs, okay, and if they gave you the graph x equals 2, and they told you find the slope of this graph, okay, that's x equals 2 is just the graph of a vertical line. What's the slope of any vertical line? It's undefined. Okay, we can't do this, and the reason we can't do this, well, let's pick a couple of ordered pairs on here. Okay, let's say I got 2, 1 and 2, 3 as my ordered pairs. Okay, if I try to calculate the slope between those two numbers, I'm going to get a calculation that looks like this, where the denominator turns into 0. And we can't do division by 0 in mathematics, so therefore we say that the slope in this particular graph is undefined. And that's the situation we have with the vertical tangent. If we have a graph that gets so steep that it's going straight up and down at some point, then we say that the slope is undefined, which means therefore that the derivative cannot exist at that point. Okay? So these are three locations or three places where a derivative may not exist for a particular function. Okay? All right. Are there any questions? I believe we've covered all the concepts that we need to for now on derivatives. Next time we come back, we will start looking at the certain functions that have some shortcuts so that we don't necessarily have to go through all of this calculation for every single equation that we come up with. All right, we'll see you then next time.